Hi, welcome to the second micro lecture about classification. In this micro lecture, we should first remember from previous micro lectures the types of machine learning tasks, the stages of supervised machine learning pipeline, and how to assess proper machine learning modeling. For the current micro lecture, the learning outcomes of today is that you should be able to identify the different types of machine learning, classification machine learning models, and understand the distinction of deep learning from machine learning. Our agenda for today is that we are going to define a supervised machine learning tasks as a notation, mathematical notation. We are going to explain the linear models and nonlinear models for classification. And then we are going to briefly go through deep neural networks as an example for nonlinear models. So first, let's put these notations over here. We have like x, vector x as an input space for the all possible instances. We have here like y as the output space for the all possible targets. And here the target is discrete, so we can set it's like all the possible labels. We have here a function f for the classification algorithm or the classification model that can map from x to y. We have here an instance that belong to the input space, instance small vectorized x, which is like one of the instances that can belong to the whole input space of the all possible instances. And we have here like small y as the actual or true label for one of the instances x. And this function f, which is a classifier or regressor, in our case, we are going to focus on classification. F of x is going to equal to y hat, which is the predicted label or the predicted target for the instance x. So we have here y is the actual one and y hat is the predicted one. So now let's discuss the different families of classification models. Let's start first by the linear models. And here in linear models, it's like a linear function of x. So here f is like a linear function of the x instance. So it could be something like w1 multiplied by x1 plus w2 multiplied by x2 and so on and so forth for the remaining features of x. And w here means the coefficient of the linear function. So suppose that we have a task that we have input dataset of one feature, the mass of persons, and the target is to predict whether it's like the gender is male or female. So basically here on the x-axis we have the masses of different persons, and we will want to build a linear model to classify between male and female. And basically, the linear model will be like a threshold over here. If the mass exceeds this threshold, we're going to predict male. Below this threshold, we're going to predict female. So in this case, we can call this model as a linear model. If we're going to increase one more feature over the mass, which is like the length of hair. So we have here on the x-axis the mass, on y-axis length of hair, and the target remains male or female. In this case, the linear model would be a linear combination between a weight for the mass and a weight for the length of hair. And here we found that the linear model that's separating between these two classes is going to be something like that. So here it's a straight line, not just like a threshold, it's a straight line separating between the two classes. Of course, it can make some misclassifications like this example, but it can actually separating the two classes as much as we can. In case of 3D models, actually we have added a new feature over here, which is the height of the person. Here the best fitting would be like a hyperplane, the best fitting linear model which is a linear combination of these three features would be a hyperplane separating between these two classes. So basically linear models is actually trying to find the best fitting hyperplane in n-dimensional space. As much as we have like more features or n features, we are going to find in this case the hyperplane, not just like a plane or not just like a straight line or a threshold. And one of the most popular linear algorithms, classification algorithms, is some algorithm called support vector machine, which tries to find the best linear function, maximizing the margins between the support vector instances. And other example is called logistic regression. It's actually one of the most popular classification algorithms. And actually also like linear perceptron could be one of the linear algorithms. So we have a family for different linear algorithms, and these are some of these examples. For nonlinear models, we are actually trying to find out not a hyperplane, not a straight line or a plane. Actually, decision boundary for these models are nonlinear. And one of the most popular families for these nonlinear models are decision trees. Decision trees have many different variants, but here is like a diagram for one of the models of decision trees for a car recommendation system. Here, like if the feature of the color of the car is red, we are going to actually recommend the car. Not red, we are going like here start to find if it's like another color. If it's yellow color, we are going to recommend. Otherwise, we are going to recommend not to buy. If the car model is greater than 2010, the model year, we are going to recommend to buy it. Less than 2010, we are going to find out how much mileage does it cover. So it's basically like a set of business rules over the features, and these business rules construct the decision tree model that can make the classification model of the car recommendation system. And of course, these set of rules actually construct a nonlinear model over the input space that we have. Other types of models could be like ensemble models, and ensemble models is actually a group of different machine learning models which we utilize them in order to make the final prediction. And we have different types of ensembles. And of course, like ensemble models are actually a group of different models, so the final outcome or the prediction of this ensemble is a nonlinear function. So basically, we have examples for the ensemble methods as majority voting, which make a weighted average of the predictions of different models. We have actually bagging, which is an average of multiple versions of the same model, training on random splits of the training data. We have boosting, which is like a sequential learning from the same model, where each model tries to fix the errors made by the previous models. So these are three categories of different ensemble methods. And of course, these ensemble methods can be considered as nonlinear models. Other examples of nonlinear models could be the Bayesian machine learning, where we start explicitly by including the domain knowledge as a prior inside the Bayes rule. We have here like the model likelihood, we have the prior knowledge, we start to train our model over our training set and try to find the posterior by generating the predictions at the end. And example of that could be Gaussian process or Bayesian ridge regression, Bayesian ridge regression as a type of the regression algorithms. And in this case, like this type of machine learning classification or regression is one of the nonlinear models. Finally, we have also like artificial neural networks, which is like a multiple levels of tries to learn like multiple levels of representation to model the relation between the input space that we have and the output. But the what can characterize the artificial neural networks and deep neural networks is that it performs automatic feature selection, extraction, and modeling, not just like modeling. This like transformation from the input space to the output space can be considered as an automated step for feature extraction and selection. So artificial neural networks are just like a collection of simple trainable mathematical units that collaborate together to compute a complicated function, which like of course would be end as nonlinear function. So actually these units are actually the perceptrons, and these perceptrons were discussed first by McCulloch and Pitts, who published the first mathematical model for a neural network. And actually, they discussed that this perceptron itself is actually a linear part, but we add an activation function after each perceptron in order to collect the input results or the weighted average of the inputs to the perceptron and then make it with a nonlinear function. And actually, this has like a mapping similar to the biological cell. So basically, we have here the input from different features. We have different hidden layers with the different weights and coefficients for the artificial neural network representing the perceptrons. And we finally have the predicted output, which is a combination between the last hidden layer, and the last hidden layer has its output from a combination from the previous layer, and so on and so forth. And for each perceptron, as we said, it will be like linear combination for the inputs from the previous previous layer perceptrons, and then we pass this output into a nonlinear activation function. So at the end, it could be considered as a complex nonlinear model. Here, like we have an example for a classification neural network where we have the input is the pixel values for an images for cats and dogs, and the aim of this network is to be trained to predict whether the image is cat or dog. So when defining the artificial neural network, we have the input data, we have the model of the deep neural network, and we need to also define an optimizer function and cost function. The cost function over here is the something that we are trying to minimize in order to make accurate predictions. And based on the predictions of this model, we calculate the cost function, start to calculate the gradients and feed these gradients into the optimizer algorithm that start to update the model weights and coefficients in the perceptrons in order to make accurate predictions in second iteration. So in training or fitting neural networks, it's done actually in iterations or what we call as epochs. And in each epoch, we are trying to use the optimizer, or in each iteration, we are trying to use the optimizer algorithm in order to update the model weights based on the feedback from the model predictions and the cost function. So deep neural networks actually use or follow a universal approximation theorem, which is that a forward neural network with a single hidden layer containing finite number of neurons can approximate any continuous function, however its complexity. So why we need like to have many different layers, even if like a single hidden layer could be enough? So basically, as you can see here, we have two different classes in this example, one for the O class and one for the X class, and the separation between them could be represented by this complex function for the green function over here. If we perform some transformation over this dataset by like making this fold of the paper, we are going to find that the model is going to be like more simple than the first one. And if we are going to make another fold by this way, the model at the end would be like much more simple than the first one. And this like the basic idea of deep neural networks is that like from a layer to the other, we are going to make some feature transformation or some folds, and these folds make the problem of finding a function that separates between the classes is much an easier task. So as we said here, we have the input space, and from hidden layer to another, we are going to make some transformations until we found out that the output space can be like easily separated by a simple function. And as you can see here, as a rule of thumb, like as we go further with the number of layers and the number of parameters, we are going to have a better accuracy. So here we have like a neural network with 11 hidden layers has like better accuracy than the networks with just 3 hidden layers. So when to use like simple machine learning algorithms and when to use deep learning, of course, like as we said, we have linear and non-linear machine learning algorithms, and deep learning could be considered as nonlinear. So when we have relatively small volume of data set or training set, it's better to use machine learning because deep learning requires large volume of data in order to train a good model. Otherwise, it will be highly susceptible to overfitting. If we have domain experience or domain knowledge to do the feature engineering ourselves, it would be, of course, better because deep learning perform like automated feature engineering, which could be like less interpretable to the user. So if we need to have better interpretability or explainability of what's going on inside the algorithm, it's better to use machine learning. And of course, like machine learning has faster execution in general, but deep learning could be suitable for complex tasks, which has complex relations between input and outputs like computer vision and NLP tasks. We have different types of deep learning architecture, just to mention them, like as we mentioned some examples over feed-forward neural networks, which is suitable for the tabular data. We have also convolutional neural networks suitable for computer vision, recurrent neural networks suitable for sequential data like time series and machine translation. We have also some other versions like graph neural networks and attention-based neural networks, which boost the performance in many different tasks. As a rule of thumb, we can say that simpler models are more able to generalize well on new data. Complex models are going to become like overfitted over the training set if the training set could be easily separated by linear models. So if linear models have good performance, why to go for complex models? So if we have like two different models, support vector machine, deep neural network, support vector machine has 98% of accuracy, deep neural network 98.2. If this like 0.2% is not like big difference, so we can actually use the support vector machine better because it means like it's more simple. So how to choose your model? Start with a single model out of each family from the families that we have described. Start to explore your space of the different algorithms. You can actually use also some automated machine learning tools to get some recommendations for the best algorithms, and then start to focus on some of these algorithms or families and exploit their search space of hyperparameter tunings more and more to find out the best performance that you can get from these algorithms. To recap this lecture, you should be able to identify now the different types of machine learning models families and understand the distinction between deep learning and machine learning. As hands-on, in the tutorial followed for this micro lecture, we are going to explore how different classification models act from some linear and nonlinear models. We are going to find out how the decision boundary of linear and nonlinear looks like. And by the end, you will understand the strengths of each approach and know when to use linear or when to use nonlinear classifiers to solve your classification task. Thank you.